Shelby Spees from Honeycomb, and today I want to talk about how we run fast and simple deployments and we observe our code and infrastructure at Honeycomb, and how we as a company have adopted with a relatively limited set of resources to make sure we can use those resources as fully as possible. Honeycomb is an observability tool, and the observability space has a lot of product requirements that are evolving very quickly. There's a large volume of data to analyze, and we have increasing demands from our users that they have on their tooling. So we need to be able to both ship fast and maintain our quality of service without compromising on one or the other. Like I said, we're a small team, so we have to be very deliberate about where we invest our time. Honeycomb's goal as a product is to help you run your systems humanely without waking up in the middle of the night and without making you tear your hair out trying to figure out what's wrong. The way we do that is by ingesting your system's telemetry data. We make it easy to explore that data and then allow you to ask ad hoc novel questions instead of limiting you to pre-aggregated queries. We allow you to ask questions of anything you might think of. Then we make sure those queries run performantly enough so that you as an engineer feel empowered to understand what's happening in your systems. That's not an easy problem. On top of that, we comfortably deploy on Fridays. We deploy every weekday and we avoid deploying on weekends. Here's what that looks like. This graph shows the number of distinct build IDs running in our systems per day. We ship between 10 and 14 times a day, and this is what high agility looks like for a small team with only 12 people. We're not a 10,000 person organization shipping hundreds or thousands of times a day. The amount of work we ship is necessarily limited by the number of people on our team. But what it's not limited by is our deployment processes. And that's a great place to be. It doesn't happen magically, and it doesn't happen overnight. Let's talk about what it took to get there. And it involved a roadmap of deciding what do we want to do and how are we going to do it. It was important to invest in the right set of tooling, what made a good fit for us. We didn't need to adopt all the shiny alphabet soup. It would have been counterproductive, and it would have slowed us down to require every engineer to think about, okay, how do I make the Kubernetes work? That's not a good use of our engineering bandwidth. So since we knew every decision would significantly impact our small engineering team, we needed to be thoughtful about what open source tooling and vendor tooling we wanted to adopt, as well as what we wanted to write ourselves as greenfield projects. And there weren't many greenfield projects. On top of the tech, we also had to adjust our cultural processes to reflect our values. We want to prioritize high agility on the product while also maintaining reliability and figuring out that sweet spot where we maintain both. This requires continuous improvement, which means addressing the entropy that inevitably takes hold in our systems, proactively looking at what's slowing us down from shipping, and investing our time in fixing that when it starts to have an impact. We're not talking about chrome polishing, we're talking about spending our engineering brain cycles where it will have the greatest impact. This requires having the relevant information to know what impact each change will have. So today I want to talk about 4 things that our continuous delivery process gives us at Honeycomb. First of all, it allows us to ship product quickly, which is important because we're in a fast-moving product space. We also want to be able to safely make changes to our infrastructure while maintaining reliability. Our continuous delivery process also allows us to embrace the risks we want to take as a business while mitigating impact on our customers. And finally, it allows us to never stop improving. We maintain a list of things we'd like to improve at the right time. And since we have a team of awesome engineers who really care about making a great product, the last thing we want to do is stop them from coming up with ways to make our product even better. So let's look at how this works on the product side. How do we go about turning lines of code into a live service in prod? We practice observability-driven development. We instrument as we code. Before we even start implementing a feature, we ask, how is this going to behave in production? And then we add instrumentation for that. Our instrumentation generates not just flat logs, but rich structured events that we can query and dig down into the context. we don't just stop there either. We lean on our tests to give us confidence about the code long before it hits prod. You need both meaningful tests and rich instrumentation, not just one or the other. On the UI side, we use this awesome tool called Storybook, which does visual testing. It's great for React. If you try changing one component, you've ever done this where you get all these unwanted cascading effects. In our case with Storybook, if you change one component and you only want to change that component, Storybook's test will fail if you end up with these unwanted cascading effects, which makes upgrading our React libraries a lot less scary. We intentionally factor our code to make it easy to use feature flags, which allows us to separate deploys from releases and manage the blast radius of changes. We can roll out new features as no-ops from the user perspective, and then turn on the flag asynchronously from deploys in a specific environment for a canary subset of traffic, and then roll it out once we're confident about it working correctly. However, we have a single build, the same code running across all our environments. The only difference is our feature flag configuration. We use Circle CI to build and push, and I love this view in Circle CI showing how long each step takes and what depends on what. On top of that, we want to get a signal on where our bottlenecks are. So we instrumented our builds to send their data to Honeycomb. Here you can see that our Go tests are fairly fast, and those dependencies take almost no time to install, versus the JavaScript dependencies installation for Poodle takes way longer than the Poodle tests themselves. And that's how we lean on tooling to make our integration steps more humane, because build time matters. Once a build is green, we perform human review as well on every PR, even the seemingly trivial ones. That way, we never need to ask the question like, should this get a review? How small is too small? We just blanket review all of them. And the thing is, you do want small PRs. Think about your audience, your reviewer, make it easy on them. And as a bonus, that helps you have a super fast turnaround on your PRs. This union of human and technology is what makes our team a socio-technical system. You need to pay attention to both. So I made sure our CI robot friend gets a high five. Once the CI is green and the reviewers give the thumbs up, we merge. No, wait until after lunch, or let's do it tomorrow, or wait until Monday. We merge and automatically deploy every day of the work week when we're ready, when the PR person is ready. I'll talk more about how our code auto-updates across environments and the situations when we'll do a rollback or a pin on a specific version. And finally, we bring it full circle. We observe the behavior of our change in production using the instrumentation we added back at the beginning. We check right away and then also a little bit later to see how it's behaving with real traffic and real users. So I mentioned that we have multiple environments. Our production environment is where customers send their data in order to observe their systems. The instrumentation we write in Honeycomb sends data from production to a second environment that we call dog food, because at Honeycomb, we eat our own dog food. So we can observe how production behaves with real user traffic and real user data. This query shows, for example, how many times our users are visiting the SLO page, which can tell us about adoption rates on that feature. We do this when we roll out new features and ramp up traffic on that to make sure not only is it behaving right, but do people actually want to use it? Then we have a third environment called Kibble, where we send our telemetry from dog food, so we can observe how our code is behaving in dog food and what our users are doing there, which in dog food, our users are Honeycomb. We'll often turn on feature flags for experimental features in dog food, which means there's a higher chance that'll fail. This way, from Kibble, we can observe the failure modes with real users. I want to be specific, dog food and Kibble are not staging environments. All three environments run the same code, the same build ID. So that's how our team of a dozen engineers can deploy 12 times a day. You may be familiar with the 4 key DORA metrics and the research published in the Accelerate book. These metrics aren't independent data points. You can actually create positive virtual cycles among all of them when you improve even one of the metrics. Let's start by talking about lead time. You push a commit, there's something wrong, you fix the build failures, the new build succeeds. Our build process runs on every single branch, the same process across all branches, all the time, automatically, and it reliably takes less than 10 minutes. Since your PRs are small and you plan ahead to make them easy to review, you can often get a review in about an hour. So then do the math, it takes about 3 hours from pushing a commit to your change running in production. Lead time is so important that last year we actually switched CI providers because our build time started creeping up. You can see in the graph here, and it was slowing down our engineers. You want tight feedback loops. Once you have a really short lead time, now you can deploy more frequently. There's your second DORA metric. We use cron jobs to update the build every hour when there's a change, and that gets rolled out across all 3 environments, staggered 15 minutes apart. We smoke test using kibble and dog food, but again, they're not staging environments. Once we hit merge, the deploy train rolls out. If something goes wrong, we also keep a set of recent builds that we can roll back to. You just point to the previous build, and it updates and rolls out across all our environments. Since we already run CI on every single branch, we go into deploying with a very high level of confidence about the quality of our code rolling out. And we already heavily use feature flags. So we can use flag flips and fix forward fairly quickly rather than needing some special emergency rollback procedure. I believe we had less than 3 bad changes in over 2,500 changes last year. So that's how you lower your fail rate. Finally, our time to restore goes down. For something that's fixed by turning off a feature flag, it's fixed in 30 seconds. In the event that turning off the feature flag won't resolve it, we can point to a previous healthy build and have that running in less than 10 minutes. If we need to fix forward, that's just reverting the commit on GitHub, waiting for the new build to happen, and then pushing that out to our machines. It's not an onerous process. And this is what high productivity product engineering looks like. By starting with lead time, we're able to create a virtuous cycle. By starting with lead time, we're able to create a virtuous cycle. We're able to deploy more frequently, have fewer changes fail because our tests are more likely to catch things, and mitigate the impact of outages when they do happen. Well, so far, I've only talked about changing individual binaries. Let's talk about the infrastructure side. As infrastructure engineers, our job is to empower the product to succeed and support the business. It's not about padding my resume, adopting Kubernetes for the sake of adopting Kubernetes. The goal is to build systems that are reliable and simple. We want to allow the product to shine, so we create an environment where the product will succeed. And you need to start where you're at. Every team has their warts. It's okay to start from an ugly place. What's important is coming up with concrete steps that you can take to move forward. If there's a process you're doing over and over, that's the stuff you want to automate. Don't make humans do boring, repetitive work. Computers are great at it. That way, the humans can invest their brain cycles in working with the value stream. There are also things that are working okay but are suboptimal. We have to be proactive about fixing that duct tape that's holding our systems together, and over time, replacing it with more durable forms of infrastructure. At Honeycomb, we've had our fair share of duct tape, but we prioritize replacing that piece by piece, and it's really paid dividends. We have to have reproducible environments. There's no dangling infrastructure changes, no custom configuration anywhere. That hygiene is an important part of running resilient infrastructure. So how do we apply this at Honeycomb? We don't use Kubernetes in a load-bearing fashion, although we do use it for some auxiliary helper jobs. Our environments that serve traffic use raw VMs, which are simpler to maintain and reason about. That really matters when you're a small engineering team. We use what some would call boring tools. If we need to kill a VM, a new one gets cold booted from Chef, and the Chef script just updates every hour. So we don't have to worry about establishing a container-built infrastructure, and as I mentioned before, the latest binaries get pulled on a cron. Those binaries are stored in S3. We're already busy running a distributed column store and query engine, so we're not going to go out of our way to build generic blob storage. We use utilities in the cloud so we can focus on our core business. All our infrastructure is code under version control. All changes are subject to peer review and go through a build process. It's like gardening. You need to be proactive about pulling weeds. This way, we never have changes in the wild. On top of that, we use cloud services to manage our Terraform state. We used to have people applying infrastructure changes from their local dev environments using their individual AWS credentials. Now, with a central place to store those changes, we can, for example, limit our human AWS user permissions to be much safer. We use Terraform Cloud, and they're kind of the experts on Terraform. We don't have to spend a bunch of engineering resources standing up systems to manage our Terraform state for us. They already have a handle on it. This also lowers the bar to making changes. A new engineer joins Honeycomb, and they can open a PR to create their AWS user directly in the GitHub web UI. They don't even need to clone the repo. Using cloud services to manage state means we can diff infrastructure changes directly in the browser and easily share those diffs within the team. No copying and pasting Terraform plan output from your terminal. With a human approval, we release directly from the browser. This is an example of when we started using on-demand spot instances and wanted to ramp up production traffic. Liz's tiny PR is perfect. It's very easy to see what's supposed to change. In Terraform Cloud, it shows exactly how that change, that new infrastructure differs from the reality in our AWS environment. And back in GitHub, we can see that the build's passed and it's a valid Terraform change. We also automatically sync our configurations in AWS with the head of our main branch in our Git repo. That way, we don't have to worry about infrastructure config diff or drift over time. Changes only happen in GitHub. It's easy to accidentally shoot yourself in the foot with infrastructure changes. You don't want to be tearing down your entire AWS environment with the wrong command. Like, we don't even want the possibility of that. So we set up guardrails, and we make sure there's always at least one copy of critical processes running on VMs in our infrastructure. That way we're not accidentally resharding, we're deliberate about when we reshard our storage. Since all these changes are subject to peer review, we don't need to bug on call every time we change our infrastructure. Only the riskier changes do we say, hey, let's pause and watch this to make sure it works. And once we're happy, we go back to business. We deploy our infrastructure changes incrementally to reduce the blast radius. We're able to do that because we can deploy multiple times in a day. There's not a lot of manual overhead. So we can test the effects of changes on our infrastructure with much lower risk. This relies on having modern components and being able to keep up with the latest versions, which is another great thing about using cloud services. We don't have to do a bunch of work to roll out Terraform version upgrades. Continuous delivery of infrastructure as code means you can't be afraid of making changes. If you're afraid of that, your systems are going to be brittle. And we use feature flags on our infrastructure. We can turn on or off AWS Spot in our auto scaling groups, and feature flags allow us to say, hey, under special circumstances, let's stand up a special fleet. If we have a misbehaving user, we can then quarantine that traffic to a subset of our infrastructure. So then we can observe how their behavior affects our systems with CPU profiling or memory profiling, while also preventing them from affecting our other users. Oops. This also gives us the confidence to delete unused components and code. If you're nervous, wrap it in a feature flag, turn it off, observe that change across environments, and then go back and delete the code later. Having automated infrastructure state management also makes it easier to refactor our infrastructure code. Of course, we can't prevent all possible errors. Bad things happen in the real world in production. For instance, see that dip in the graph? I'll zoom in. You can see the traffic dropping as an entire cluster falls over piece by piece until we have a complete outage for about 10 minutes. Then we revert to a previous healthy version and we can start serving traffic again. So how bad was that? How do we measure that? We use service level objectives, SLOs, which you may or may not have heard of. we do some math to help us define what is successful, what is healthy. SLOs are a tool we use as a team internally to talk about service health and reliability. The math we do starts with a number of eligible events. So for example, eligible API requests. Among those API requests, a good event will be one that returns a status 200 within 100 milliseconds. That's considered good. Our availability, our level of success is what percentage of the eligible events are considered good, how many of our eligible events actually return a 200 status within 100 milliseconds. And then we measure that level of success over time within a rolling, for example, 30-day window. Our error budget we create by subtracting from 1. So the error budget we can use internally for talking about risk, and I'll talk about that a little bit more. We use our SLOs to alert on user pain specifically. When we're not meeting our success targets for good events within a window, that's when we alert. You may be familiar with numbers of nines. At Honeycomb, we use different numbers of nines for different services. Our ingest is really important. We don't want to be dropping customer data, so our strictest SLO is 4 nines for ingest. When you go to the home page of our UI, we want those dashboards to load quickly. So we set our SLO for default dashboards at 3 nines. And finally, we want to return queries quickly, but we're not as strict about this. So we want 99% of our user queries to return results in less than 10 seconds. So here I've added a caption to the graph from earlier. It says user data throughput. This is our ingest. We dropped customer data for 10 minutes. That's pretty bad. We were able to roll back, but that required human intervention. So what did we do? We communicated to our customers and we were honest about what happened and what we were doing to address it. Maintaining that trust with customers is really important. Our error budget for a 30-day window allows for 4 minutes of downtime on ingest. 10 minutes of downtime meant we burned through 3 times our error budget. In response, we took some steps to reduce risk. We halted deploys and investigated what happened. And in the incident review, we realized that we had checked in code that didn't build. That shouldn't be a problem, except we were in the middle of changing CI providers, and our CI was using some experimental build wiring that didn't catch when the code didn't build. So our deploy scripts ended up deploying empty binaries. And at the time, we didn't have any health checks and we didn't have automated rollback. I told you earlier that every team has warts. In this case, our warts cascaded together to create an outage. So we reprioritized stability and we didn't ship new features until we addressed all 4 of those contributing factors. We mitigated the key risks, and then once we addressed them, we went back to building. So what's ahead for us? We want to be more reliable and scalable, and so we keep focusing on continuous improvement. We want to be able to launch new services easily, and if you follow this QR code, you can see how we've launched new services in a blog post. We also want to save money, and so we experiment with our infrastructure to see if we change over to spot instances, that saves us a lot of money. And we want to continue modernizing and refactoring and keeping our systems up to date and proactively addressing entropy. That allows us to sleep easily at night. We only page our on-call person, and the on-call shift is about once a week. We only page them once per shift. We've tied together a lot of good practices that you've heard about in other contexts. And what I like about Honeycomb is that we're living evidence that you can do on-demand pushes even on a Friday and have it be safe. You just need to make the right investment in reliability. So you can do this too. Start where you're at and go step by step. Check out our blog. We talk a lot about the changes we make, the experiments we take, and our priorities when addressing business risks and business outcomes. And the main takeaway I want you to have is go incrementally forward. Add CI to one system or microservice and start there. Let the virtuous cycle open up your bandwidth and remove the bottlenecks. Here you can find me on Twitter. Follow honeycomb.io/Shelby to get the slides from this talk, and reach out. I want to talk to you.